Reinforcement learning, often abbreviated as RL, is a fascinating area within machine learning that focuses on teaching agents to make optimal choice in a given environment. The way this works is by rewarding the agent for taking actions that lead to favorable outcomes. Let's break that down a little further. At its core, RL revolves around a few key elements. First, there's the agent. Think of the agent as the entity that makes decisions. It could be a robot navigating a maze, a program playing chess, or even a self-driving car learning to handle real-world traffic. The agent is always at the center of that decision-making process. Then we have the environment. This is the setting or context in which the agent operates. If we stick with the self-driving car example, the environment would include things like roads, traffic lights, other vehicles, and pedestrians. It's everything the agent interacts with while attempting to achieve its goal. Next are the actions. Actions are essentially the choices available to the agent. For the self-driving car, these could include accelerating, braking, turning left or right, or even staying put. The agent evaluates these options based on the information it has about the environment. And finally, there's the reward. Rewards are a form of feedback, essentially a scorecard that tells the agent how well it's doing. For instance, the car might receive a positive reward for maintaining a safe distance from other vehicles and a negative one for running a red light. Over time, these rewards help guide the agent toward better and more effective decision making. What makes reinforcement learning so powerful is its trial and error approach. The agent starts without knowing the best course of action and learns through experience, gradually improving as it interacts with the environment. It's an iterative process, and the key lies in striking a balance between exploring new actions and exploiting what it has already learned to maximize its rewards. By structuring the problem this way, agent, environment, actions, and reward, RL provides a framework for solving incredibly complex problems, from optimizing supply chain to mastering sophisticated games like Go. The possibilities are as vast as they are exciting. The learning process in reinforcement learning is what truly sets it apart. Let me walk you through how it works. The agent begins its journey with little to no understanding of the environment. It starts by exploring, trying out different actions, sometimes at random, to see what happens. It's a bit like learning to ride a bike. There's some trial and error, a few stumbles, and a lot of figuring out what works and what doesn't. Now, every action the agent takes leads to a result. This result is communicated through a reward, or, in some cases, a penalty. For instance, if the agent is navigating a maze, finding the exit might result in a positive reward, while bumping into a wall could lead to a penalty. These rewards and penalties are the environment's way of saying you're on the right track, or try something different. Here's where it gets interesting. The agent doesn't just store this feedback passively. It actively uses it to adjust its behavior, refining its understanding of which actions are beneficial and which are not. Over time, this iterative process helps the agent become more skilled, consistently choosing actions that lead to higher rewards. The ultimate goal of reinforcement learning is for the agent to develop what we call a policy. A policy is essentially a strategy, a set of rules or a model that tells the agent what action to take in any given situation. It's the culmination of everything the agent has learned. The policy might start as something crude and inefficient, but through repeated exploration and learning, it evolves into a powerful tool that enables the agent to make decisions with confidence and precision. At the heart of it all, this process mirrors how we as humans often learn, by doing, reflecting on outcomes, and improving over time. Whether the agent is learning to play chess, manage energy consumption in a smart grid, or control a robot arm in a factory, the principles remain the same. It's a dynamic and adaptable approach to problem solving that has endless applications. Reinforcement learning has found its way into a wide variety of fields, showcasing its versatility and potential to solve some truly complex problems. Let's take a closer look at a few key applications. First up, gaming. RL has gained significant attention in this space, with AI agents not only mastering games but excelling at them in ways that even surprise human experts. Think of AlphaGo, which famously defeated a world champion in the game of Go, a feat once thought impossible for machines. Or consider AI in video games, where RL is used to create opponents that adapt to a player's strategies, making gameplay more dynamic and engaging. Then there's robotics. Here, RL shines in teaching robots how to perform tasks that require precision and adaptability. For instance, robots can learn to walk, grasp objects, or even assemble products on a factory line. These aren't just hard-coded instructions. The robots learn through trial and error, adapting to new environments or unexpected challenges. In healthcare, RL is making a meaningful impact by optimizing treatment plans and managing patient care. For example, it's being used to develop personalized medicine strategies, where treatments are adjusted dynamically based on a patient's response. In critical care, RL algorithms can help balance competing priorities, like administering the right dosage of medication while minimizing side effects. Moving into finance, RL is transforming trading. Automating trading strategies to maximize returns is a classic problem of balancing risk and reward, and RL's ability to learn from dynamic market data makes it an ideal fit. Over time, these systems can adapt to market conditions, offering strategies that are both responsive and forward-looking. And finally, let's talk about self-driving cars. This is one of the most visible and impactful applications of RL. By interacting with a simulated or real-world environment, autonomous vehicles learn how to navigate roads, obey traffic laws, and make safe driving decisions, even in complex situations. RL helps these systems improve over time, making self-driving technology safer and more reliable. Each of these applications illustrates the incredible flexibility of reinforcement learning, whether it's achieving superhuman performance in games, enabling life-saving advancements in healthcare, or driving innovation in robotics and transportation. RL has proven itself to be a cornerstone of modern AI. It's exciting to think about what comes next. To wrap things up, let's reflect on the advantages and challenges of reinforcement learning. Like any powerful tool, RL comes with incredible potential, but also its fair share of hurdles. One of the standout advantages of reinforcement learning is its ability to tackle complex tasks purely through experience. RL agents can learn to solve problems that are too intricate or dynamic to be pre-programmed. For example, mastering a strategy for a game like Go, or learning to control a robotic arm in unpredictable conditions. Another major strength is its adaptability. RL thrives in environments that change over time. Unlike static systems, an RL agent continuously learns and updates its strategies to remain effective, making it ideal for dynamic fields like robotics, autonomous systems, and finance. And importantly, RL doesn't require labeled data as opposed to supervised learning. Instead of relying on large annotated datasets, the agent learns directly from interaction with the environment. This is a game changer for tasks where collecting labeled data is impractical or even impossible. However, these benefits don't come without challenges. One of the biggest hurdles is the immense computational power RL demands. Training an RL agent often requires significant resources, from powerful hardware to extensive simulations, making it less accessible than other machine learning approaches. Another limitation is the learning process itself, which can be slow and heavily reliant on trial and error. While this is foundational to RL's approach, it also means that achieving an optimal policy can take a great deal of time and patience. Lastly, RL can struggle with rare or unseen scenarios. Because it learns from experience, an RL agent might not be well prepared for edge cases or situations it hasn't encountered before, which can limit its effectiveness in safety critical applications. In conclusion, Reinforcement learning is a fascinating and transformative area of machine learning. Its ability to tackle complex dynamic problems makes it indispensable in many fields, from robotics to healthcare. But to unlock its full potential, we must address its challenges, from computational demands to its sensitivity to rare events. As researchers and practitioners, we're only beginning to scratch the surface of what's possible with RL. The future is both challenging and exciting, and RL is sure to be at the forefront of AI innovation.